this awesome workshop. And today I'm going to be talking a little bit about energy storage based on the conversation we just had. I think people are pretty excited. Um, but we're going to talk about, I'm going to talk about energy storage in the context of microgrids and remote applications. And there's a bit of a difference between when we think of energy storage for grid level, like the full-on hydro-grid utility versus smaller microgrids. Some of my presentation is going to be a little bit repetitive, or there's going to be overlap with the other presentations. So apologize for that. But before we get into energy storage, I really want to talk about why we need it. And so, as it's been mentioned before, a lot of these remote locations, they rely on hydrocarbons for energy needs. So you got your diesel generator, your propane, and your gasoline generators. But there's of course issues with that. You've got the emission side, the carbon emissions, but also the sulfur dioxide and the nitrous oxides. But then there's also the kind of local emissions that happen with it in the sense that you've got operational emissions. It's noisy, it's fumes. A lot of these communities, maybe there's 50, 60 people in there. If this generator's going off all day, how does that affect students at school, for example, or at nighttime when people are trying to sleep? And Also, there's we briefly just talked about the cost to transport and store fuel up north or in remote areas. Um, so there's a lot of issues with using diesel and other hydrocarbons, and so this idea of using renewable energy, so solar and wind, paired with energy storage, to really address these issues. And so that's what we're going to talk about today, and I'll give a brief overview of all the technologies that are available today. Um, the technologies that are available, quite diverse. We see a small tidbit over here. And so uh, before we go into the technologies themselves, I really wanted to kind of frame how we look at these technologies. So the three things I'm really looking for are the technical performance characteristics, which we'll go into, also the economics of it. And then each one of these technologies, based on the laws of physics, you've got certain quirks with it and where it's best used. So you got advantages and disadvantages. So what I've done is I've broken down these storage technologies into how the energy is stored at a physical level. So on the far left, you've got electrochemical. So in this particular case, you've got from the electro side, you've got the electrons literally being stored as electrons. Either they're stored as electrons in batteries or capacitors, or they're stored within the chemical bonds, in flow batteries and hydrogen. The second type of energy storage is looking at the thermal side. So we've talked about this just now, storing that as heat, but also storing it as the chemical chemical bonds that can release heat or absorb energy in their systems. And then on the right-hand side, we've got mechanical. So this is storing energy as potential energy or kinetic energy, and then extracting that as needed. In terms of the performance characteristics, when we think of technical performance, we really want an even playing field to compare these technologies. So there's the big four that we look at. So the first one is power density. That's megawatts per meter cubed of this technology. So how much power can we deliver? So we think of, let's say, an LED light. They're pretty low power. So if we have a whole bunch of them, you can get away with using an energy storage technology that is not a high power, does not have a high power density. Now you compare that to, let's say you want some sort of heating system that needs a lot more power. And so you have to pick and choose your technologies based on the use case. The second big item is energy density, of course. How much energy can we store? And this is where hydrocarbons keep defeating everyone, right? So hydrocarbons are incredibly energy dense. This is one of the reasons why they're so popular. Batteries and other technologies aren't just there yet, but there's a gradient. Some are better than others. The third one is cycle efficiency. How many times can you keep using this technology until it deteriorates and cannot be used? And then the last one is lifetime. How long will this storage technology last? So, oh, sorry, I mixed that one up. Sorry, lifetime is in cycles is, how long will this technology last? The more you use it, the more it deteriorates. Cycle efficiency is how much energy is actually returned back to the user after using it the first time. And on the right, of course, we've got our economic characteristics. You've got capital cost, operating cost, and stuff like that. Now, compared to hydrocarbons and the tools that we need to use them to burn them, the cost for all of these technologies really depends on the application and the technology itself. And then there's an aspect of maturity, technological maturity that goes with it. So we'll start kind of talking about all of the ones I listed earlier. I'm not going to read the text over here, but I will talk about it at a high level. And so when we think of batteries, so it stores energy through a reversible reaction. Think of batteries more like a sponge, and the electrons are just kind of going all the way through the sponge, right through the sponge. So in terms of the power density, very high power density, that's why they're so popular. But when it comes to the energy density itself, a lot lower, which is why your electric vehicles, electric vehicles only more recently can compare to gasoline vehicles just because of that lower energy density. In the last 15, 20 years, I'd like to say that cycle efficiency has really improved. Before, batteries weren't that great, but in the recent past, there's been a lot of work in that to get back as much energy as you put in. And then in terms of the technology itself, these are great. So they make these batteries in C cans or whatever, or they can install them in C cans, and then you can just kind of expand it in a modular fashion. But as great as that is, where do you use it? If you think about a colder place, a lot of these remote locations are colder. The degradation of that battery pattern completely changes, and so the use case really depends on the location as well. And then finally, in terms of cost, expensive now to manufacture them, but once it gets going, it's a pretty there's not a whole lot of maintenance cost to it. Now we compare batteries to, let's say, capacitors. And so a capacitor, I just explained a battery as a sponge with electrons all the way through it. And a capacitor, the electrons are hanging out only on the outside. So instead of a thick device with electrons all the way through, capacitors are more individual plates with in parallel with a lot of electrons in between them. They work great. They can give you really high power densities, just like batteries, even more. But because they're independent plates in parallel, their energy density is a lot lower. In terms of the reliability and durability of these things, metal plates with electrolytes, they're quite reliable, and they have really long lifetimes. But because they have low energy density, they're best suited for short duration, high power applications. So think of, let's say you've got this example little town, and they've mostly battery powered, which can take care of 99% of the load throughout the year. There's always going to be a little peak here and there. Those peaks can be sorted with through capacitors, right? Again, expensive now, but once it gets going, it's pretty cheap to maintain. There were two other ones, flow batteries and hydrogen, but my colleague is going to talk about them in detail later, so I won't go into that. So we're going to talk about the next type, which is that heat battery, which everyone really had fun talking about last time. So I apologize if I'm a little bit repetitive. But yeah, as it was explained before, you've got a medium like water or sand or molten salt, and you use, like you said, like a glycol loop to collect heat from elsewhere and store it in there. This particular figure over here, it shows the reservoir of heat to be like a natural feature. That's great if you can have one, and that's actually one of the things that makes it cheaper, especially for grid scale. But when you're looking at like a microgrid, it's going to be more of that heat battery stuff, right? On the second bullet, I'm saying the power density is irrelevant. That's a bad word. It's not irrelevant. It's just hard to really quantify the value of heat when it's trying to offset electricity, unless you're using it directly for electricity, right? But as the discussion we had, there's so much waste that happens when converting heat back to electricity. It makes more sense to use heat as is. And Pascal, I think you mentioned that like the synergy is a lot better that way. Based on the material, so if you're using sand, for example, the cycle efficiency is pretty high. and the lifetime is also not too bad. The challenge is this is a slow system. The heat is stored, and so by the time you got to get it going, it takes a little while. They're bulky, of course, and then over time, despite how good the insulation is, there's always going to be a little bit of heat loss. Capital cost, again, high because you need these big units that can hold sand or whatever, and it depends on the material itself. But again, I mean, how much do you really spend on maintaining it? Now we compare that to a thermochemical thing. And the best way to describe this one is when you're going skiing or hiking, you got those little gel packs, right? Same thing. So what's going on there is you got sodium acetate, and we click the button, starts a reaction, an exothermic reaction, and then there's heat coming out of that. Once the reaction ends, that if you've ever used those packs, the pack becomes solid. So you got to put it back into boiling water, boils it, and then energy goes into the sodium acetate and then changes it back into liquid form to be used later. Same thing in terms of all the other characteristics, very similar to the thermal system. The challenge is instead of using sand, now we're using sodium acetate or other chemicals. So toxicity, how can we use it in a microgrid location? And then also, how expensive are these materials? And because it's a more recent technology, there's more research that needs to be done in order to get cheaper ones. Right? Same thing again, slow to respond to, and also there's the aspect of bespoke integration within the system that you're using. And then those were the thermal side, and then lastly, we're going to talk about the mechanical side. And so there's, of course, the three. You've got flywheels, compressed air, and then pumped hydro. Flywheels are actually one of the older energy storage technologies that we have. Think literally a wheel that's flying, and you've got a generator slash motor that spins. It either speeds it up when it's collecting energy from renewable energy, and then stores it as velocity, and then when it needs to use it, the motor switches to a generator form and takes some of that kinetic energy out. In fact, that's the system they use in hybrid vehicles when they're recharging the hybrid battery when you're using a braking system. Very powerful, very high power density, but in terms of the amount of energy that can be stored, you're going to need some pretty big flywheels in order to store a lot of energy. The physics of it is great. There's not a whole lot of there's no chemicals in here. So even though there are moving parts, it is a pretty robust system. So very good in that sense, but you have to think about a big, heavy flywheel. If it's a steel, you want it robust, it's got to be heavy. That thing's spinning pretty fast. The likelihood of that thing exploding is pretty low. But if it does, or when it does, because maybe there's too much energy in the system, the effects can be pretty catastrophic. So if we're thinking about a small community with a flywheel system that's not underground, that is above ground, there's some inherent dangers with that. So something to consider when it comes to energy storage in that context. Pretty moderate capital cost. There's no expensive chemicals going on over here, and then operating cost is also pretty low. The next one, compressed air. Similar philosophy. You've got this energy coming in. Instead of spinning in a wheel, you're just using that to power a compressor, and that compressor is taking air, atmospheric air, and then putting it into an air tank. These things are a lot cheaper when you have a salt or an aquifer that you can store this air in, or a salt cavern. But when you start storing them in tanks, they get a lot more expensive. The other challenge with this is this is also a pressurized system. So when you think of a diesel generator, the diesel combustion part is pressurized, and so yeah, that's dangerous, right? In a compressed air system, the entire loop is compressed, and air is not fun when it's under high pressure. So there's a lot of safety considerations with this one. The other one you have to consider is the turbines and compressors themselves. When you seal them, you can't use regular gaskets. You have to use seal skids, and the fluids that they use in that. When they get, if there's a leak and there's the air gets and there's contact with the sealing fluid with high temperature air, it generally goes past that auto ignition temperature. So there's always an explosion risk with these things as well. Something to consider when you're in a small community. And then finally, we've got our pumped hydro. These are basically, think of regular hydro power plant, but in reverse. Again, generally a lot cheaper when you have an existing reservoir, but can be used instead of a reservoir if we have just a water tank, like a city water tank. Could just pump water up during the day using a pump, and then at nighttime use a turbine to bring that water down and generate electricity. Great in theory, great in practice, except since you're dictated by the size of the reservoir, if it's an artificial reservoir, the cost can really the greatest cost to energy ratio or power ratio really are seeing at those natural reservoirs, not so much with the artificial ones. And so that's basically at a very high level the technologies that we've got, other than the ones that Sophie you're going to be talking about. So I wanted to open it up to some questions at this point.
This is super interesting. Thank you so much for putting all this together. Do you have a capital cost per megawatt hour for these?
Off the top of my head, no, but there is. Now, it really depends where you apply it. So when you look at the literature for the pumped hydro systems, most of the literature is going to be talking about existing reservoirs, like natural reservoirs, and they'll give you super low costs. No one's talking about the artificial tank, right? Same thing with the compressed air storage. So it really depends on the situation where you do it. In terms of the technology itself, pretty cheap technologies, but that whole system cost, yeah. Any other questions?
Go, Elise and I can both
Sure.
present, and then we kind of got a full picture of storage.
Sure. I think there's one question in the back there.
I'll ask it after the
Sure.
storage.
Okay, awesome.
Or,
No, it's general storage.
okay.
Sure. Okay, awesome. Thank you.